Okay. All right, so today is the final lecture for wrapping up this first module. And yeah, I had planned to actually use the stylus on this machine, so I have a blank slide. But okay, anyways, so today we'll wrap up sort of our discussion on Uppaal. And if you have not received this email already, the final assignment of this this second module is out today. It's actually a pretty short assignment. It's just 3 problems. And I'm going to walk you through exactly what you have to do in this assignment, right? So far, in the previous lecture, we discussed what is Uppaal, why it is such a powerful tool. Today, I'm going to walk you through the heart model plus the pacemaker in Uppaal. So that's going to be quite a complicated thing, and so we'll try to understand that in the first place. And then we will look at LTL specification and how you can check a LTL specification for this composed system which has the heart model and the pacemaker, sort of what we really started out in the beginning of this module. So I think you can still follow along with me. So if you just go to the course web page, so if you can just say Principles of Modeling for CPS. So on the course web page and also on the assignment that has gone out, you will see assignment 7 at the very bottom, and then there's a template file associated with this assignment. So if you download that template, it will contain a XML file which you can import into Uppaal. And what this XML file has, it has some predefined templates for the heart model. So you don't have to draw it just like we did in the last time. That was only for our understanding. Today we will directly jump into some of these templates that are present in the XML file, and to follow along what I do, just go ahead and download this template and import it into Uppaal. Okay, so I'm going to jump into Uppaal right away. So what I have done is I went to File, Open System, and then what you have in the template is hm1.xml. I'm uploading the solutions to mine because I have to show you some stuff. But what you have to turn in for your assignment is essentially the solution file. So it's already open, so I won't play with it. And when you open it, what you would see is a bunch of different sort of templates, right? So in the previous lecture, we saw only a handful of templates, at most 2 in one of the sort of the examples that we saw, where we had a simple timed automaton, where we looked at the non-determinism, and then the mutex one, where we instantiated different objects of a single template. So today I'm going to walk you through what the heart model looks like and the pacemaker model looks like in Uppaal, and it looks very different, which is why on first glance you might be, as always, you might feel that I talk about something and then I show you something completely different, but I will again show you that functionally it is equivalent to what we have been looking at. Right, so some of these template names should be familiar, like an atrial node and a ventricular node. So just a little bit of a context of how we are going to structure the heart in Uppaal. So in Simulink, you did this worksheet 5, and I released the solutions just prior to the lecture today. And in that, the at most complex model that you built was, let's say, a node, a path, then another node, another path, and then another node, right? So we had the atria node, a path, then the AV node, or the atrioventricular node, then another path, and then the ventricular apex, or the right ventricular apex. So you have this NP, NPN configuration. I think in one of the extra credits, we also had a Simulink block for a pacemaker, and it was connected to the A-pace and V-pace and A-sense and V-sense signals of the NP-NPN model. So the whole idea was that we had this single Lego block of what a node automata is, and we copy-pasted that to whatever we want to model and just tweaked the parameters. So somewhat similar principle applies here, except that the nodes themselves will look a little bit strange and different to you, and then I will try to explain why that is the case. So there's no easy way to transition into this. Let me just show you what I'm talking about, and then let's just walk through that. So if I click on the atrial node template on the left-hand side column, This is all of the atrial node in Uppaal. And sure enough, it looks very different from what the atrial node looked in Simulink. So what's going on here? Let's just try to read or understand this timed automaton. First of all, it only has one location, rather than this notion of rest and ERP and RRP that we spend so much time understanding. So this is essentially a more permissive way to model the sinoatrial node. So what is the property of the sinoatrial or the SA node? Let's recall that the property is automaticity, that this node can self-depolarize in the absence of any neighboring depolarization. So let's try to see, even though there's a single location, we have three sort of transitions. So let's try to understand what is going on in this node. So let's first double click on the initial state itself. We have an invariant called x less than equal to a max weight. There's some parameter or timer called maximum amount of time that you can remain in your initial or ready state, right? So the state is called AR ready, which is the name right here. And the invariant is x, which is perhaps a clock of this automaton, is less than a max weight. So let's look at this transition where you have a guard condition and a synchronization and an update. So if I double click on this red transition, we have a guard that x must be greater than some minimum value. When that is satisfied, you can issue a synchronization message called aget. You can think of aget as like asense. And then there's an update that you reset the clock. So if you just pay attention to this transition and the invariant, what we are essentially saying is that between the time a min and a max wait, you can depolarize at any time you want, which is already very different from the way you model this in a deterministic Simulink model. So recall in Simulink, you had defined some rest period, and as soon as that rest period timer was consumed or ran to 0, we issued some activate path message back in the day, which seems like a couple of months ago. It was just a few weeks ago. So, but the heart is not this machine, right? It's not such, it doesn't run by the clock. In reality, the behavior of the atrium, especially as seen from the pacemaker, would be of the form that there is some interval of time within which the atria, at any time within that interval, they can depolarize. They will not always depolarize at 150 milliseconds as defined. It could be anywhere from 100 milliseconds to 400 milliseconds, for example. So that's what we are trying to capture here, that any time between a min wait, when this transition is enabled because the guard is satisfied, but no more than a max wait. Why no more than a max wait? Because the invariant forces you to go out of the location. That's the job of the invariant that we discussed in the example last time. So all this is really capturing is that the SA node can depolarize between some range that you will specify based on the patient, a min wait and a max wait. Now you can definitely ask, what happened to all the story of ERP and that we shouldn't acknowledge some retrograde and pacing signal when we are in ERP? So as shown, this automaton on its own does not solve this problem, but I will show you how in conjunction with some other nodes and paths, it will still prevent that particular situation where you cannot depolarize when you are in ERP. Okay, so on its own, this does not solve that. But let's look at the other two transitions as well. So we first say that, okay, you can self-depolarize. So this sort of edge from A ready to A ready has these guard synchronization and update. And all this is saying is that between this range that you provide, you can self-depolarize. But what's the other situation where the atria might have to depolarize? Well, one situation is if there is retrograde conduction. And so that is captured using this loop. So if you receive an activation from the path, you also reset the clock and depolarize. And finally, there's this only another possibility, whether the depolarization signal is not due to your automaticity, it is not due to the path. There's only one more possibility, that it is directly being paced with the pacemaker. and that loop is here. So if you listen to this atrial pace or AP signal or synchronization, you can again reset your clock and depolarize. So functionally, it is responsive to the three things that we expect the SA node to be responsive to. We expect it to be automatically depolarizing between some range rather than a specific time instance of clock. We want it to be responsive to synchronization or actions or messages from the path, and we want it to be responsive to a direct message from the pacemaker. So any questions on what this automaton is trying to do? I know there's questions on why this is equal to the Simulink one, but let me see if there are any questions on the first part. Do you all just see what this automaton is trying to do? Okay. So similarly, the ventricle node is exactly the same as the atrial node. It has the same transitions. Only difference is that the signals are named according to the ventricle. So the ventricles can also self-depolarize in the extreme case, when nothing is happening, then the ventricle can take over the heartbeat momentarily. That's nature's plan B or plan C. So in this case, they issue their own sort of V-get signal. Now, I'll be the first one to admit that it doesn't help that these signals are also named differently than how they were in Simulink. But at least the notation is consistent that when you issue something, it's followed by an exclamation. When you are listening to something, it's followed by a question mark. So again, this loop says that the ventricles can also self-depolarize between V min weight and V max weight. And just out of curiosity, what do we already know about these intervals? What do you think the interval of the ventricle or the value of V min weight and V max weight, how do they relate to the values of A min weight and A max weight? Are they larger or equal or smaller? Larger, right? Because the ventricle never really takes over the beat of the pacing of the heart. And remember how we also discussed that you can set the exact rest period to some 9999 seconds or some large number. Similarly, you can do that here if you want normal sinus rhythm. And similarly, when you do get an activation message from the path, in this case, since this is the ventricle, this would correspond to antegrade conduction. You do reset your clock, and if you get a direct pacing signal from the heart, from the pacemaker, you also reset your clock. So far so good, right? So although they are not visually same as our Simulink picture, we do have the same sort of input-output response, if you will, for these automatons. So now comes the problem, okay? So in Uppaal, what we are going to simulate the heart as is not going to be NPN. Right? So previously we have the SA node path, AV node path, ventricle. In Uppaal, in this implementation, so by the way, this doesn't mean this is the only way to do it. This is one way to do it. In Uppaal, our implementation is going to be SA node, AV node, path, and ventricle. So we are skipping one path between the SA and the AV node. So even though we think that all nodes are similar, when I show you the AV node, this is what is going to respect the ERP properties of the atria in some sense. Okay, so let me show you what I mean by that. And this is my implementation of the atrioventricular node in Uppaal. So once again, on first glance, it's like, what is going on, right? This has nothing to do with any of the automatons we have looked so far. But again, the way to navigate your way out of this is not to panic and just look at every transition, right? So we get into this habit of now reading what this transition system is doing by simply exploring that. So at start, we are in our ideal location as the atrioventricular node. This is not the path, remember. This is the AV node. The job of the AV node is twofold. It's to add a delay and to slow down the conduction. And in this case, the AV node is preventing this back propagation, or it is, you can see visually we have added an explicit ERP state just in the AV node. So you can actually think of your heart as, in Uppaal, it's both the SA node and AV node which together are preventing this ERP depolarization problem, where we want that if the heart or the atria is in ERP, then you shouldn't accept a depolarization signal. So let's look at what's happening in the AV node. By default, you are in idle. So let's look at this transition, the first one. If you receive a polarization signal from the atria, so who is issuing A get? We just saw that the atria is issuing A get when the SA node self-depolarizes. So that signal is tapped on or listened to by the AV node. It resets its own clock and goes to an intermediate state, which I haven't labeled. I can add a name to the state, but it's fine because it doesn't really denote anything physical. So it reaches some intermediate state, which is committed. So can someone recall what committed means? We just saw that in the previous lecture. A committed state, what does that imply in Uppaal? Anyone remembers? Yeah. Right. So a committed state is if you enter the state, you have to get out of it. So it's like another way of forcing an invariant without really giving an invariant condition. So you listen to the signal from the atria, and then what should you do if you are the AV node? You should propagate that signal forward. Right? So you listen to the signal A get, you issue your own signal called atrioventricular depolarization or AV, and then you enter your ERP state or location. In ERP, we use the same trick. So we will keep using this trick forever, that you can remain in ERP for this range between AV ERP min and AV ERP max. So everything is now in terms of ranges and not in terms of specific clock cycles or clock times, which is why this is a more realistic / more permissive model. So because in some situation, the ERP period, when the person is exercising or something could be small. When they are not, when the metabolism is slow, it could be large. So we allow for both just by incorporating this range. So after you are done with your ERP, you go back to idle. But what else can occur? Another thing that can occur is that you were in idle and you directly receive a pacing signal from the pacemaker. You should again issue your own depolarization message here. So that's what this second transition is happening. So first of all, let me tell you why I have added a committed state. It's not required. I could have said that you can have two synchronizations. One is what you listen to and the other is what you issue, and they could both occur on the same transition. I only added committed states here to make it more interpretable for you, right? So that these two things are happening when, what is the cause and what is the effect? Think of it that way. So again, you can also depolarize. So the effect is causing your depolarization or synchronization when the pacemaker is issuing atrial pacing signal. So if you are the AV node, you can get triggered by the SA node or the atria. You can get triggered by the pacemaker. So can anyone guess what is this outer loop for? What is the third possibility for the AV node to get depolarized besides the SA and the pacemaker? Retrograde conduction, excellent. So if there's a retrograde conduction, you also, so who will issue this? We will see in a bit. A path is going to issue this. But if there's a retrograde conduction, you go into another sort of loop where you are issuing a activate message. And who was listening to this activate message? The atria was listening to this activate message in its own retrograde cycle. So the AV is talking to the atria in this manner. So although this visually looks nothing like what we have seen before, even it doesn't even look anything like the atrial and the ventricle node, it is incorporating the ERP of the entire atria in one of its loops. So we are almost there. We are getting very close to all the desired habits of the heart, except one, which is this conduction delay. We haven't really seen that. So the final piece of our heart model is this template called conduction path. And this actually believe it or not, is the closest to our Simulink view of the world. Where you are in idle, the path is idle, right here is the initial state, double concentric circle in Uppaal. Based on the direction from which it gets its depolarization signal. So who was issuing this AV signal? The AV node, right here. It issues a AV signal, AV signal. So if we are in antigrade conduction, you are idle, you get the AV signal, you go into your antigrade location where we do the same thing. You can remain in this conduction delay between some value T conduction min and T conduction max. Same trick. But again, we are implying that there's a range of values. So when you come out of antigrade or take this transition, you can issue a message to activate the ventricles, right here, this message, VACT. And so who was listening to VACT? The ventricle node is listening to VACT right here in its retrograde loop. So the conduction works in our retrograde example. We have just seen this loop. What is this loop? If you were in antigrade and you get a retrograde signal, they cancel out, right? Remember how we spent a lot of time in Simulink doing that. So it goes into this intermediate dwell state that is same as conflict or wait in Simulink. So I won't go into the explanation again. But what we are saying is that you have to come out of dwell state for no more than, like, you can spend 2 time units here, but nothing more. Okay, so we have studied antigrade. This is the business as usual antigrade loop. This is the simultaneous propagation. Similarly, I'm saying if you were in antigrade and the pacemaker tried to pace, that's also sort of a simultaneous propagation. So let's ignore that. We'll not entertain that. And on the other side, if you get a retrograde signal, so the ventricles polarize first, then you go into retrograde conduction, you can remain within some interval between T conduction max and T conduction min. You can even use different variables for antigrade versus retrograde. Here I think it's the same variable. And when you come out of retrograde, you issue VA, which should be listened to by the AV node, right? VA, this is retrograde. So the conduction works both ways. The only difference is that if you are in idle and you received a pacing signal from the pacemaker, you go into retrograde. If the path was idle and the pacemaker depolarizes or paces the ventricles, then we are forcing a retrograde conduction, so we respond to that. So any questions so far on these templates of the atrial, ventricle, AV and conduction path? Any questions? If you have any doubts over why this is the way it is or how is it different from Simulink? So we can go all over this again. This is what the atria was like. Very, very different from Simulink, but more permissive in functionality. Ventricle is the clone of this with different labels. The AV node is the one which has a dedicated ERP to prevent some sort of back propagation stuff. And the conduction path is more or less the same with a special provision for accepting signals from the pacemaker. So any questions? We'll see the entire heart model and then it'll become more clear. So how do we, let's actually look at that since I just mentioned it. So just like our examples from last time, let's go to system declarations, and we have a lot of declarations in our template. So what we are doing here is, let's look at this part right here, or not even that. Let me just look at this. So here I'm instantiating objects of the class where the name of the class is the template that I just showed you. So HRA is the atrial node with the correct name of the signals, and this is the definition or the arguments which is equal to the A min weight and A max weight. So I'm saying that anytime between 490 and 500 milliseconds, the SA node can depolarize. So I'm not giving it a single value. Similarly, the ventricle node is just a large number compared to the SA node. The conduction path, so look, I'm doing a trick here. If I actually want the conduction to be a single number, I can set the min weight and the max weight for T conduction to be the same. And effectively, I'm not giving it any range. I'm forcing it that when time progresses and becomes 150 milliseconds in the conduction delay, you go out of your antigrade or retrograde state. And then I have initialized the AV node as well. So if you see carefully, right, so I said our sort of structure is the atria, AV node, conduction path, and ventricle. That's the heart model. So if you look at, let's say, 500 milliseconds of the atria, plus 150 milliseconds of the delay, plus 350 milliseconds of the AV node, altogether they are 1000 milliseconds. So effectively, there are 3 nodes which are capturing this phenomena of the SA node depolarizing, going through the AV node to prevent with the ERP, and the conduction delay before it reaches the ventricle. Okay, so this is just like any object-oriented program. I've created 4 objects, each of them corresponding to the correct arguments that I pass. So you don't have to change them during your homework, not at least the name of the signals. You may have to play with the values of the min and the max weights. So we have these 4 objects. Let's create a system now which has all these 4 objects. I've already created many systems, so I'm going to comment out this one, and this is my heart simulation. So now I have a system which is just composed of the 4 objects that I just created. So this is now just a Uppaal question. What do I do next? What should I do next once I declare a system in Uppaal? What do you do next? You run the syntax check if there is any errors. So we go to tools, check syntax. There's a lot of warnings, but there's no errors. Now we can load this system right here into the simulator. It will, okay, it was already loaded, but if not for you, it will ask you if you want to update it. And so this is my heart model. We have a high right atrium, which talks to the AV node, which talks to a conduction path, and then that talks to a right ventricular apex. So this is my NNPN model in Uppaal. And to convince you further, let's walk through some of these transitions, right? So, so here I can, so you can pay attention to this trace on the bottom right. So let's take the first transition where the atria will self-depolarize, or the SA node will trigger. So you see the SA node, which is this high right atrium, HRA1, it sends this value A get to the AV node, which was in idle. And what should happen to the AV node? It should enter its ERP, which happens here. And in doing so, it has propagated that signal forward to the conduction path using a synchronization called AV. So the conduction has now gone from idle to antigrade, just like what you expect, right here, from idle to antigrade. So you remain in antigrade conduction, and then when you come out of it, you go to dwell, and in doing so, you issue a depolarization message to the ventricles, where they will now take the loop of antigrade within the ventricle. So we started from ready, idle, idle to ready in the ventricle, and now we are at ready, ERP, dwell, and ready in terms of the trace. So each of these is the location in which the automaton is. So we are not done yet. So the path has now come back to idle, and finally the AV node has also come back to idle. So this is really where we started from. Ready, idle, idle, and ready is exactly the same as where we started from. And all these flow of messages tell you how you have completed one single heartbeat in this normal sinus rhythm. So how do you know? What is this notion of time? So in the middle panel, you have all these values of the parameters that you either instantiated or the values of clocks, right? So global variables, we'll come to that in just a second. But let's say in the AV node or in the SA node or the right atrium node, we have A min and A max, which is the same value that I sent it when we were declaring the object in the editor. But what is important is there's this field called constraints. It is essentially going to show you the value of the clock in each of these locations, right? So when we started out, the clock could have been between 0 and 500. This is the global clock. And after one beat, if I highlight this, the value of my clock is anywhere between 980 and 1000, meaning that roughly we have 1 beat per second. Because this much time has elapsed for me to go over the transitions, which take me from the atria to the ventricle. So this is the transition from the atria to the AV node. This is from AV node to the path, and this is from path to the ventricle. And now back to the same trace. So questions on, if you are convinced whether this is normal sinus rhythm, or any questions in general. Let me pause. Yeah. This is the global clock. Yeah. If you were looking at any of these clocks, there's like HRA clock is this, AVN clock is this. So you can examine any of the clocks in their individual automatas as well. But already, this is different from your Simulink view of the world, where you were looking at scopes. And sometimes it's not easy to associate which scope line corresponds to which cause. But here, this is very explicit. You can track down which signals are being sent, what transitions are they causing in which automaton. And so from electrophysiology, we know that this should be the progression of a normal sinus rhythm, and indeed, that is the case. So if we can do normal sinus rhythm, we can do a lot more. Okay, so just like how we did NSR in Simulink, and then there was a homework exercise to do variations, we will do something similar here, right? So let me go back to the editor. And here, in addition to defining like the regular object or instances of these templates, I have also defined two special cases. I have defined an instance of an atrial node such that the weight intervals, A min weight and A max weight, are half of what they were, or roughly half of what they were in the normal sinus rhythm. So I am saying that your atrial node is highly likely to self-depolarize much quicker because it's half the rate. Can anyone remind me what this condition is called when the atrial node polarizes much faster? What is this condition? It's tachycardia. So this is everything else being the same, I can create a new object called HRA2, high right atrium instance 2, which is exactly the same as high right atrium instance 1, except I'm forcing it to give it a shorter duration, or the likelihood where it will self-depolarize. Right, so all I need to do now is go back to my system and just change this to HRA2. And if I go to, hopefully there's no syntax errors, but now when I go to the simulator and update, visually it will look the same thing, except that now the A max weight and A min weight have been updated. So here's another cardiology question or heart condition question. If I reduce the interval, the waiting interval of my high right atrium to be half of normal sinus rhythm, I expect that within the same duration as a normal heartbeat, I would have 2 activations of the atria on purpose. So what do you expect the heart to respond like? Do you think the 2 activations of the atria are transmitted as is to the ventricles, and the ventricles will also follow the atria with this sort of fast beats? Or do you know something about the art which will prevent this condition? So in other words, let me, since we are pseudo cardiologists here, does atrial tachycardia cause ventricular tachycardia, or is there some natural defense against that? And you actually did this for one of your homeworks. Yes. right? So remember, if you did this exercise, which was also called the 2:1 conduction, if your atria goes into tachycardia, it will pace twice as fast, but this is where the antegrade and the ERP of the AV node will come into play. That not all these fast paces or depolarizations from the atria will be transmitted through the ventricles. In fact, what we expect to see is, for roughly every 2 atrial depolarizations, there should be 1 ventricular depolarization. So once again, I can kind of simulate my system by just going next transitions. So you see, we start from sort of the same idle as normal sinus rhythm. We get A get, this is sent through, and it reaches the ventricle. So at this point, the ventricle has activated from the first atrial beat. And notice how the AV node is in ERP, the path is actually idle. And now, since AV was in ERP, this message is not received, this next A get, or this next depolarization. Once again, the trace view of Uppaal makes it super easy to see why it wasn't received. So you can actually see that you are issuing A get because of this tachycardia in the high right atrium, or fast depolarization, but it is getting ignored because the AV node was in its ERP. Okay, so we have this. This was the second A get which we haven't responded to. Oh, yeah. So we go next. Now we are back to our initial state where we started from. Ready, idle, idle, and ready, and we are back here. So the next atrial beat should be accepted. So you can keep going that once 1 out of every 2 atria polarizations is going through the AV node, and 1 is getting blocked because of this AV block, or 2:1 conduction. Why 2:1? Because I deliberately made it half. I could have made it whatever, 3:1, 1.5:1, or whatever. So moral of the story is, all I did was create another instance of the atria which was initialized with some tachycardia-like parameters. So let's do the opposite of that. So can someone tell me what would this atria correspond to? Bradycardia, where it's the exact same node, but I'm instantiating it with double the values of this normal sinus rhythm, roughly double, not exactly. So I want that this time the pacing of the atria becomes very slow, between 800 to 1100. So if I now go back to my system declaration, all I have to change is my atria object. And I know that there's no errors, so jump to simulator. We have HRA3. Now notice something very subtle here. We know that HRA3 is this bradycardia causing specialized designed atrium node by instantiation of the parameters. But if I just simply look at the trace, so only pay attention to, I never actually look at what's going on here. I always look at this box because this tells me everything I need to know of my automaton or system. So if I go next, A get to now AV to conduction, conduction to ventricle, and back to the same. So if I only look at the trace, this looks exactly how normal sinus rhythm would look. You cannot tell it that this is bradycardia because we are not skipping any unnecessary or ill-timed messages. So the trace is actually exactly what normal sinus rhythm is. The only way to tell there is bradycardia is if you are in your final sort of after 1 beat and look at the value of clock. This will tell you that yes, the 1 beat took roughly 2 seconds rather than 1 second, which is what bradycardia is. So really, one way to think about Uppaal is that time is not like in Simulink. It's symbolic time. Time is a range in Uppaal. Why is it a range? Because of the way your automatons have been designed. So you think of what this is saying is that In all possible transitions of this heart model, when you have 1 beat of bradycardia, for all traces, this much time would have elapsed. Any value between 1600 and 2200. We allow for all possibilities. So which is different from how we sort of simulated things in Simulink, where we considered everything like clockwork. So questions on how do you create a heart model? You compose it out of these blocks. These blocks are instances of templates. These templates we just went over. You may want to revisit the video to convince yourself again why they work. And then you can just input the appropriate object into your system and emulate or simulate that condition. Good? Any questions? Okay, so let me show you something of a different flavor that you may not have seen before, but that would be the first building block of our pacemaker. So here in your homework as well, there should be already included a template called MON-LRI or monitor LRI. So what this is, so can someone remind me, if someone remembers in pacemaker study, what was LRI or lower rate interval? Let's see if you can recall. Anyone remembers? Which beats? You are almost there. It's actually the ventricle beats, but you're correct, right? So the lower rate interval was that what's the minimum amount of time the pacemaker will allow to elapse between 2 V-cents. So in other words, if I don't see a V-sense after some time, I have to intervene and pace myself. Because remember how we briefly discussed how, comparatively the atria, not atria, I created a new chamber. The ventricles pumping is sort of more critical than the atria pumping, because they are the ones which send the blood to different vital organs of the body. Just relatively speaking, both are critical. So the LRI is the minimum duration that we want to elapse before we have a V-sense or between 2 successive V-sense. And so what this automaton is a monitor to calculate the time between 2 successive ventricle beats. So this automaton monitors the time for other automatons. We actually saw an example of this last lecture where we had a loop and the reset was being done by a monitor when we discussed this notion of whether the clock can be more than 30,000 and whatever. You may want to go back and look at that too. So this automaton is a monitor to monitor the lower rate interval or the ventricle to ventricle duration. So let's convince ourselves how it is doing that. It starts by being in this weirdly named state called wait first. But this is the initial state. We can call it whatever. What are the 3 things that can be picked up as a V-sense or a ventricle depolarization? Either the ventricles depolarize by themselves, which rarely occurs, but we allow for that possibility, or they depolarize because of the activation from the path, or they depolarize because of the pacemaker. Those are all the possibilities for the ventricles to depolarize. On each one of them, we transition to another waiting state called wait second. And notice how on each one of them, we are starting a timer t equals 0. So think of this as the first instance, whatever be the cause, you transition and start a timer. Then you have the exact same transitions to another state 2a on the next instance of whatever is the cause of the V-sense. So after wait second, you can again have the 3 possibilities that the next V-sense could be either because of the path, because of the ventricle node itself or because of the pacemaker. And so whatever is the cause, we transition to another state called 2A. And here's my assertion that the value of the timer in 2A, when you enter it, is going to tell you how much time has elapsed between successive ventricular beats. Just follows logic, right? Because when did we start the timer? We started the timer on the first beat, whatever is the cause of it. Then we transition again. We don't mess with the timer, it's still running, but we will transition the second time we see a V-sense. So when we get to this state, how much time would have elapsed? The value of this clock T would have been the time between one of these transitions and one of these transitions, or two successive V-sense. And this is a committed state. So in the next instance, once we have logged that value of time, we can go out and reset. And now we don't have to go back to the first one. We can just use this loop to keep track of the clock. And this clock will always tell me the time between successive V-sense. So convince yourself or ask questions whether this indeed is monitoring the time elapsed between any ventricular activity, but successive ones. Right? In the very first case, so you can think of all of this part as just the first trigger. But after that, this is enough to keep track of time. So any questions on if you are convinced this will monitor stuff correctly? Is it clear why this claim is true, that the value of time when you reach this committed state 2_A in the automaton MON LRI is going to tell me how much time has elapsed between successive ventricle events? That's the statement. So if it's clear, how do we use it? So here's the power of Uppaal again. Let me go to system declarations and comment out our regular system. And now I can instantiate another system which has the atrium node instance 3, which was my bradycardia node. It has the regular AV node, conduction, and ventricle, and it has a monitor as well. So everything is the same as my bradycardia, except that I have added a monitor. In fact, before I go to bradycardia, let me just use a regular normal sinus rhythm node. So I've just changed it to HRA1. So if I go to the simulator, now in my system, I have my heart model, which is this atria, this is the AV node, this is the conduction path, this is the ventricle, and this is the monitor, LRI, which is just keeping track of ventricular events. So we can simulate it, but I want to actually show you the verifier part of this heart model. So we don't have a pacemaker yet, mind you. We are just monitoring heart activity. We are not reacting to it yet. So what would be a good property to verify? So we've already loaded something into the verifier. So let's go over it together. What this is saying is, for all paths, and you can read the comment, I'm literally reading it out. For all paths in this complete model with 4 heart nodes and 1 monitor. So for all paths in my system, it is always the case, because of these square brackets, that if you are in the location 2A in the monitor, which we just discussed, it will imply that the value of the clock in the monitor is less than some TLRI value. So first of all, where is this TLRI value defined? If you go back to your simulator and look at global variables, we have defined a timer here, right here. TLRI is equal to 1000 milliseconds or 1 second. In other words, I have defined a global variable, And what I'm asking is, in this system, in normal sinus rhythm, when my atria node is behaving as is it always the case that for all paths means this big A, it's always the case that if you are in the location 2A, this location in my monitor, then the timer of this monitor must be less than or equal to 1000 or 1 second, which is this constant that we define. So what do you think for normal sinus rhythm? Should this be satisfied or not? In other words, for normal sinus rhythm, we are checking whether the V to V interval will always be 1000. So what do you think? Satisfied, not satisfied? So first of all, here's an opportunity to appreciate Uppaal. You cannot mentally or manually figure the answer out. I hope that's obvious. We cannot, in your head, figure out this transition and then this transition. Why not? First of all, we allow for non-determinism in these cases. And then secondly, we also have symbolic time, where time itself is an interval. It's not a correct value. And we haven't really discussed how we kind of translate or simulate the system when time is a range. So the only way actually to know for sure is to go through the verifier. Intuition does inform us that if you are in normal sinus rhythm with these parameters, right? The parameters of your normal sinus rhythm are these right here, which kind of sum up to 1000 that we've already discussed. So intuition tells us that yes, it should be the case that there is no reason why you wouldn't respect a 1 second V to V interval. But I am asking for all paths, for all possible cases, always. So the only way to verify is using model checker. So let's check this property. It is indeed satisfied. So what this is telling you, there is no trace in my system where the monitor will observe a V to V interval which is longer than the constant value of TLRI, this value right here, which is equal to 1000. You can play with different values too. In fact, I think in the worksheet you have to play with some different values. So very quickly, if I go back to the system and change this to a bradycardia node, where the heart rate is slower than 1 second, right? So all I have done is change HRA1 to HRA3. 3 is my coding for bradycardia. And now let me turn on the diagnostic trace to, let's say, shortest. Now, if the heart is in bradycardia, the single beat takes more than a second. We just saw it takes roughly 1600 to 22, any value in between. So it should violate this LTL requirement, that the V to V interval is never exceeds the 1000 TLRI value. So if we check the property now, the property is not satisfied. And now if you go back to the simulator, it has loaded a trace, which is an example of a set of transitions such that the value of the timer in the monitor is going to be more than 1000. So I can replay this, and you can see how these values change. It's hard to follow because the replay is occurring at a high speed. But at the end of the trace, let's look at the value of the LRI timer right here. So when I highlight it, it becomes less visible, so I'm highlighting the one below it. So the value of the clock T in the automaton monitor.LRI is anywhere between 800 and 1100, which means there is a trace where it will be greater than TLRI. So therefore, this property was violated. So I see some blank faces now, so I'll literally pause for a minute and let me know what are your questions or concerns. So let's start with, is it clear what is the monitor trying to monitor? What is the monitor automaton trying to monitor? Is that clear? Any questions on that? What is it trying to monitor? It's trying to keep track of how much time has elapsed between successive ventricular events. And that keeping track means that we can literally read the timer of that monitor. We can literally read the value of this timer T when we reach this state. And by design, this will tell us how much time has elapsed. And what I showed you was, if I create a system which was just normal sinus rhythm, and I tried to check, is there any case when this time between successive V2V events is greater than some threshold, where the threshold is user designed. In normal sinus rhythm, the checker returned no. There is no possible trace. And it makes sense because we have designed the values of the rest periods and the wait times such that they all add up to 1,000 and no more than 1,000. But in bradycardia, when your heart rate is slow, it is indeed expected that the V2V interval would be more than regular normal sinus rhythm, which is 1,000 or 1 second. Yeah, Aaron.
So I understand why this property is not satisfied.
Yeah.
But when you showed us that clock value, you said it was between 800 and 1,100.
Correct.
But that's about 60 beats per minute, isn't it? Between 800 and 1,100?
But look at the property. The property says that the timer value has to be less than or equal to this value, which is 1,000.
And I understand that.
Yeah, so if it,
It seems to me like this bradycardia example is fairly close to an actual normal sinus rhythm. If that's the time between V to V, is about 1,000 milliseconds.
right. So
That sounds like normal sinus rhythm.
sure. So it is not. It is not. You're right. So it's not severe bradycardia as per the clock, and we can make it more severe by playing with the timing properties. But I think the take-home message for this part is to understand why it was not satisfied, and the trace does make sense, because you can also reason that the LRI should be actually more than 1,000, because 1,000 is normal heart rate. So I think that may be the problem here, that the TLRI is defined to be 1 second. It could be 1.5 or something like that. So your observation is correct. Yeah. Okay. So final example, just so that when you open up your homework, you know what is going on. In your homework, you will have a model which now has everything. You have a monitor, you have the 4 nodes of the heart, and then you have a pacemaker too. In fact, I have given you the templates for the pacemaker, except one. Right? So this, which I won't go over, is going to monitor the A to V interval or the AVI interval, and if that is not met, it will issue a V-pace signal. Similarly, you remember how we had VRP, ventricular refractory period. If you read your kind of pacemaker worksheet as well, or in Simulink we also kind of introduced that. Now, let me first show you what we have to do for your homework. So in your homework, you will have a full system. So let me load that into here. So this has many nodes, right? So it has the heart nodes, it has the monitor, and then it also has some pacemaker nodes. Now what I want to show you is the output of your homework. Okay? In your homework, you will create a system in bradycardia and add these pacemaker objects to it. Some of them are defined for you, right? So I'm defining. You don't have to create this monitor. You can simply reuse this monitor. Similarly, you can reuse this pacemaker object. This one, you have to fill in some stuff for it to work. That's actually a homework problem. But the output of your homework will be a heart in bradycardia connected to a pacemaker. And what we expect now is that with this heart, which is in bradycardia, which should not satisfy the property, does the pacemaker ensure that that property is satisfied? That's the job of the pacemaker. That if you are in bradycardia, it's trying to fix that by maintaining the LRI. So this is literally the culmination of all of what we have been studying the past month almost, where we motivated the problem that how do you ensure that software on medical devices will never make a mistake? Where never means never, right? It's not between 1 million instances or 1 billion instances, it's never. And what we said was, it's a very hard question to answer. What we can answer is, if you give me the model of a system and the model of the device, I can check whether something bad never occurs or whether the device will never make a mistake. And so this introduced this notion of model checking, of this notion of automatic and exhaustive checking of whether something happens in my system or not. So indeed, if our pacemaker is right, the same property in the presence of bradycardia this time should be satisfied for all traces. Meaning that no matter what your heart does, there is never an instance where the pacemaker is not able to maintain a V2V interval. So let's see if it better be satisfied, right? So it might take some time because we have a very big system, and Uppaal takes some time for it to do its model checking. What is Uppaal doing? It's doing exactly what we studied. It's building this product automaton. It's doing this cyclic search to find a counterexample. If it doesn't return any cycles or any counterexample, it will say the property is satisfied. So what we have shown is that in this big system, which has the heart plus the pacemaker nodes, we have validated that the pacemaker will always being the keyword for all paths, be able to prevent bradycardia. And that's powerful. And this is how you design software for medical devices and prove absence of bugs. So in your homework, you are given all of this except this guy. I'm not going to click on it because that will just reveal the solution. So you are given everything except VRP, which is one of the things that you require for your pacemaker. But I have explained how you can build the VRP automaton in Uppaal. So your homework would literally be, or half of your homework is, you have to build VRP. You can, if you have built it correctly, it will use these arguments, and you have to run another property and show me that whether it is satisfied or not. So it is literally just 3 small problems, but one of them is for you to actually open Uppaal, install, and play with it. All right, so last 1 minute, let me switch back to PowerPoint. I don't know why this is called Endgame. Yeah, if you remember, actually, I had assigned some reading. I don't know how many of you actually read that PDF, but what we have implemented here is a VVI pacemaker. Okay, so pacemaker has codes of usually 3 letters. The first letter is which chambers are getting paced. So VVI means you are only pacing in the ventricle. DDD pacemaker can pace and sense in both chambers. So the first alphabet is which chamber is paced, the second alphabet is chamber sensed, and then there's a mode or response to sensing as well, which is triggered versus inhibited. Don't worry about what that means, but the Uppaal model is a VVI pacemaker, okay, just for comprehensiveness. So with that, we have concluded our second big module in this course on medical cyber-physical systems. This is just a recap of what we have covered in this sequence of, I think, about 10 or 11 lectures. We started from this idea of verifying medical devices, in particular implantable cardiac devices. But really the principle of modeling, the name of this course is Principles of Modeling. What you should have taken away from this module is this whole area of transition systems and timed automata as a way to model sequences of things or events, which is very different from the state space model that you saw in the very first part of this course. So we use the heart as the case study to understand timed automaton, but similar to how we spend so much time on parameter estimation, the analogy in this module was model checking. That's the big key principle. What is model checking? Why is it so powerful? Why is it different from testing? And what are the ingredients for you to use a model checker, right? So at the very least, I'm forcing you to use Uppaal in the hope that somewhere down the line, when the time comes for you to do some verification or model checking for your own research/career, or point someone else towards model checking, you know what is the tool or what is one of the tools. And in doing so, we have to go into the weeds. We have to understand the domain, which I always emphasize for every module. You have to speak the same language as the domain experts. So not only are you in this unique Venn diagram of people who can talk to a facilities manager and build models, there's a very exclusive group who can understand the heart and a building at the same time. I hope you belong to that group. And so we did this journey of understanding the mathematics behind a transition system, model checking. In doing so, we had a very brief, yet I hope useful overview of linear temporal logic. I know that was new for most of you, but I hope you got to understand why LTL is useful. There's many, many different types of temporal logic as well, which expand the grammar of LTL even further. But for this module, it's not a formal methods class. So it was outside the scope a little bit to go all into temporal logic alone. So hopefully, you are convinced that why model checking is useful for this very different class of CPS problem, right? So the heart, like I said, is the second most complicated object that we know of. And so to model a physiological system is very difficult because we don't know the fully deterministic behavior of that system itself. That's why we resort to these tools. So finally, starting on Thursday this week, we will begin our final module on automotive cyber physical systems, where automotive and self-driving is the sort of the domain, but the key principle that you will learn is data-driven modeling. Or we have some interesting assignments on how you can not use physics, not use any knowledge of the system, just give it raw inputs and expect model outputs to make sense. So how do you ensure that's a good model, and how do you model that to begin with is what remains in this course. So with that, that's the end of the second module. I'll see you on Thursday.